Good morning everyone. So today we will see about trees in data structure. So we will see what are all the introduction you must know about trees in data structure. So listening to that introduction, so you can call tree as a collection of nodes. A tree will be having a unique node called the root node, and from that root node you will be having number of trees that are called as subtrees. These node can be empty also. So yeah, that is a tree can be empty also. If the tree is not empty, then it will be having a unique distinguished node called the root node, and that root node will be having 0 or more than one subtrees. So in this diagram figure 4.1, you can see a general tree diagram where root is the unique distinguished node, and T1, T2, T3, T4 up to T10 are called as the subtrees. These subtrees are connected to the root using an edge. So these are all the basic things that we know about, that we must know about the trees. Then we will see some of the terminologies that we must be familiar with in this tree chapter. So the first one is child and parent. So in this diagram, A is a root node and A is having childrens from B to Q, and in that every node except the root node A will have the parent. That is, since A is a root node, it will not be having any parent, but the other nodes from the node B to Q, they all will be having the parent nodes. For example, P and Q's parent is J. Similarly, the parent of J is E and the parent of E is A. A will not be having any parent since it is the root node. So the leaf is the term that refers to a node that have no children. In our diagram, the nodes B, C, H, I, P, Q, K, L, M and N are all the leaf nodes since they are not having any children. So the next one is next term is sibling. Sibling is nothing but the nodes that have the same parent. For example, P and Q are the siblings since it is having the parent same parent J. Similarly, E is the same parent of I and J. Therefore, I and J are also siblings. K, L, M are also siblings since they are all having the same parent F. Similarly, B, C, D, E, F and G are also siblings since they are having the same parent A. So I hope you understood about what is a child, what is a parent, what is a leaf and what is a sibling. Next we will see about the term path. You can calculate the path from one node to another node by counting all the edges that occur in that path. So in the length of a path, if you count the number of edges on the path, then you will be getting a length of the path. Depth of a node, it is nothing but the unique path that occurs from the root node till the node you are going to find the depth. So they are also called as the levels. The next one is height of a node. You will find the longest path from that root node to a leaf node. That will be considered as a height of a tree. So all the leaves will be at the height of 0 and all the root node will be at the depth of 0. The depth of root node will be 0. That is, in the diagram we can see that A is at the depth of 0, B, C, D, E, F, G are at the depth of 1, H, I, J, K, L, M, N are at the depth of 2 and P and Q are at the depth of 3. Similarly, the height of P and Q are 0, the height of H, I, J, K, L, M and N are 1. Height of J is 1 since it is having children. Either you can count P or you can count Q. So this is what the height of J. The height of E is 2 since it is having two level of nodes, that is J is one level, P is another level. So this is the way how you will find the height and the depth. So the height of a tree is nothing but that is equivalent to the height of the root, and the height of the root will be equal to the deepest leaf node depth. So the ancestor and descendant, if there is no and if the node n1 is not equal to n2, in that case you can say that n1 is a proper ancestor of n2 and n2 is a proper descendant of n1. So from the diagram you can see that D is the ancestor of H and H is the descendant of D. So this is what ancestor and descendant terms. So these are all the various terms you must be familiar with in the chapter tree. So next we'll see about how you can implement trees. So the trees can be implemented in first child next sibling implementation. So each node they will be having a data. Along with that you need the edge that connect that root node to the child. So all the childrens can be represented in a linked list of tree of nodes. So A is a root node and the root node A is the first child is B, and other than B the node A is having other childrens like C, D, E, F and G. So you can represent this in the first child next sibling representation. First child means an up to down arrow will occur from A to B, that is down arrow. From A you are having one arrow to the first child B, and from the first child you will be having an arrow to the next sibling, that is the sibling of B is C. Similarly from C you will be having an arrow, left right arrow from C to D. Similarly from D to E you will be having an arrow, E to F and F to G. And these are all the way how you will represent implement a tree in first child next sibling. You will be having two edges here, one is top down edge and another one is left to right. Top down edge is used to refer to first child, and left to right edge is used to refer to the next sibling. So the left side is a general tree, and in the right side diagram you can see the first child next sibling representation. So the first child of E is I, therefore you are having a down arrow to I, and the sibling of I is J, therefore the next sibling J you are having an edge called left to right is used there. So this is the way how you will implement trees in first child next sibling representation. Though the structure of tree node is given there, you will be having an element and you will be having two pointers, one to represent the first child and another one to represent the next sibling. So this is the structure of implementation of tree nodes in the first child next sibling representation. So next we will see about the binary tree. From the name binary itself you will be able to know it can have two values, only two values, not more than two values. So in a tree you can represent binary tree as a tree in which no node will have more than two children. That is, if in the previous diagram we have seen this is a tree, but it is not a binary tree since A is having 1 2 3 4 5 6 nodes, 6 children it is having. But in a binary tree you can have at most 2 children. So this is a tree, but it is not a binary tree. So binary tree can have either 0 children or 1 children or at most 2 children, not more than 2 children. So the you can see in that diagram representation, for the root node root you are having two subtrees, left subtree and the right subtree. The next right side diagram, it is also a binary tree because it is not having more than one or more than two children. A is having one child B, B is having one right child C, C is having one right child D, and D is having one right child E. Since all the nodes are having only the right child, this one is called as a worst binary tree. So this is the introduction about a binary tree. So next we will see how to implement this binary tree in a doubly linked list. So here, as we have seen in the structure of a tree node, here also you will be having a one element and two pointers. One refers to left subtree and another one refers to right subtree, or you can call it as the root element, left child, and the right child. So trees are usually drawn as circles and they are connected by edges or lines, so that you can connect a root node with its children's. So examples for this binary tree, you can take expression trees as an example. Since infix expression, so you are having three types of expressions like infix, prefix, and postfix. Depending upon the position of the operators, you will be representing that. So in an expression tree, here they have taken a infix expression, that is the operator occurs in between two operands. Binary operators will be taken here. All the leaves will be in the, having the node as operands, and all the internal nodes you will be having the operators. So how to draw this expression tree we will see in the next slide. So suppose you are having the postfix expression like AB plus CDE plus star star. So how to construct an expression tree for that? If it is an operand, or if it is an operand, you will push that operand into the stack. For example, A is an operand, so it is pushed into the stack. Next, B is also an operand, so it is also pushed into the stack. The next thing is plus. Plus is an operator. When a plus occurs, it plus is pushed into the stack, and the operands A and B will be considered as a left and right child correspondingly. So this is the way that you can see in the second diagram. The next operand, next one is C. It is an operand, so it is pushed inside the stack. The next one is D and E. They are also operands, so they are also pushed into the stack. The next one is operator. So the last two pointers D and E are popped out from the stack, and you will frame that star as a root node, D as a left child, and E is a right child. So the next diagram will be, next operator is star. So you can see that C will be considered as the left of star and plus will be considered as the right child of star. So you will be having those diagram is left as an homework for you. And the last star is considered as a plus will be considered as a left child, and star will be considered as the right child. Similar to these steps, you can finish the remaining diagrams. So the next concept we are going to see about in trees is binary search tree. So binary search tree is similar to that of a binary tree. You can have only two nodes, not more than two nodes. Apart from that, here you are having one more property, that is binary search tree property. That is, for every node X, all the trees in its left subtree should be smaller than the root node X, and all the keys in the right subtree should be larger than the root node X. So we can see in this diagram, root node is 6. So all the values that are in the left subtree, that is 1, 2, 3, 4, all these nodes should be less than the root node 6, and 8 is in the right subtree, it should be greater than 6. The left side is a binary search tree, whereas the right side diagram is not a binary search tree. Since 7, because of insertion of 7, 7 is greater than 6, so it should be in the right subtree of 8, but here in the diagram, in this right side diagram, 7 is included as a left subtree of 6, so it is not a binary search tree. You have to refer to each and every node, like as we have seen, 1, 2, 3, 4 should be less than 6 and 8 should be greater than 6. Similarly, 2 is again a root node. Therefore, 1 should be less than 2 and 3 and 4 should be greater than the root node 2. And similarly, 4 is a root node. Therefore, 3 should be less than the root node. In this way, you will be constructing a binary search tree. So the last concept we are going to see today is a tree traversals. So tree traversals are used to print out the data in a tree using certain order. So here you are having three types of order: pre-order, post-order and in-order. So in the pre-order traversal, you will be printing the root node first, then the left subtree node, and then the right subtree node. Whereas in post-order, you will print the left node first, right node second, and the root node last. Whereas in order, the root node will be printed in between: left node first, root node first, and then the right node first. So here you can see an example for this expression tree. If you want to construct a prefix, how you will find is, prefix means root node should be printed first. Therefore plus is a root node, therefore it will be printed. Next, left side again you are having a plus, that will also be printed. After that you have to print the left child of plus, that is a. And then after finishing that, you will see star is a right child. Since it is a root node, you will print that star first, then the left child b, and then the left child c. So we have finished plus plus a b, star b c. So next, in the right subtree, star is a root node, so you will be printing that star, and then the left of star is plus. Since it is a root node, you will be printing plus. After that plus, you will be checking the left of plus, that is star. So since star is also a root node, you will be printing star. Then the left child of star is D and the right child is E. So you will be printing correspondingly D and E. And then the right child of plus is F and the right child of star is G. In this way you will be printing the pre-order traversal. And similarly, in the same case, you will be printing the post order and the in-order traversal. Post order means root node will be printed at the last. So first you will see plus is a root node, so you will not print. Again left side plus is a no root node, so you will not print. And the left side is A, so you will print A first. Then you will check the right child, whether plus is having any right child. It is having, so you will go there. Right child is star, and since it is a root node, you will not print that. It is having a left child B and right child C. Therefore you will print that. Then you will print the root node star and plus. Correspondingly, the right subtree will also be calculated. Similarly, in order traversal, left node will be printed first, then the root node, and finally the right node. So this is the introduction about trees. So we have seen today the introduction of trees, some of the terminologies you must be aware of in the tree, then what is a binary tree, then what is a binary search tree, and finally we have seen about the three different types of tree traversals. Thank you, friend. Thank you, students.